right, good morning to you all. I wanted to say just a little bit more about conjugation and fission, and then we're going to move on to the Diels-Alder reaction today. So here is the eye. Behold. We're going to focus in on a portion of the retina, and you've got rod and cone cells, and then you've got cells that communicate what the rod and cone cells see to the optic nerve. And light comes in through all of this and is absorbed in the rod and cone cells, and the photoreceptor portion is down here next to the retinal pigment epithelium. That's important. This is what helps recycle the things that observe, or the things that, this helps recycle the rhodopsin protein after it's absorbed light. So if you zoom in on any one of these rod or cone cells, you've got this really weird structure where the membrane goes sort of side to side, and you end up with these little discs. And embedded in these discs are lamellar particles that have, and they themselves are sort of lipid bilayer type segments, but within them you have the opsin protein, and it's loaded with this 11-cis retinal molecule that we learned about. The way that's linked to the protein is through a bond that you'll learn about in 352 called an imine, I-M-I-N-E linkage. So we're sort of zoomed in on these segments. These are the ones that observe, that do the absorbing of light. So this is what 11-cis retinal looks like when it's attached to the protein. You've got a lysine side chain that's forming an imine bond. You'll learn about that in 352 with the rest of this molecule. And the part that's important is the fact that you've got this cis double bond, which is less stable than the trans isomer, but you can't isomerize from cis to trans without weakening a pi bond. So we did some homo-lumo stuff last time, and we observed that the gap between homo and lumo for some molecules, as you increase the extent of conjugation, that gap gets lower and eventually gets from the UV to the visible region. So if you put 11-cis retinal into Spartan and you look at the lumo, oh wow, that's interesting. It's a delocalized long pi system, but if you look at this gap between homo and lumo, it's worth about 3 electron volts, whatever that means. But if you do the math, it turns out that the wavelength of photon that will promote an electron from homo to lumo is 425 nanometers, which is in the visible region of the spectrum. In fact, let's see, we got it? No, yes, there we go. 425 nanometers, that puts you here, sort of in the purple. All right? When light is absorbed by this molecule in the rhodopsin, that weakens one of the pi bonds. Because this is a conjugated system, it's hard to tell which one it weakens, and that allows for isomerization from cis to trans. Yeah? Yeah, how does it know to break in the middle, reform as cis? Because this is an extended pi system, it's not like the lumo is an antibond to any specific of those pi bonds. We're considering them all together. So that's sort of a hand-wavy answer, but I think the idea is that you, by promoting an electron from homo to lumo, you can think of it as though you were promoting an electron from a bonding to an anti-bonding orbital, and that weakens one of the bonds. And yeah, as to why it's that one, I would say just because that's the one that is cis and can isomerize to trans. Yeah. So this molecule is kind of spring-loaded. Its shape is curved, as you can see here, but after it absorbs light, it pops right open to the trans, and that changes the shape of the molecule. And that changes the shape of this transmembrane protein, leads to an action potential, which is translated down through the optic nerve. So rhodopsin changes its shape. That changes the binding of a G protein coupled or a G protein inside rhodopsin or inside the lamellar particle, and that generates the nerve impulse, and you see. That took an exceedingly long amount of time to explain, but you've been seeing like crazy all along. So now, you know, appreciate the importance of HOMO and LUMO because it is how you can see. Yeah?
So does it immediately then like unrelax and go back to how it was you can see again?
It's a good question. What happens after it isomerizes to trans? Yeah, actually, nature has to go in, clip out the trans version, and then reinstall a cis version into the protein and recycle it. So as seeing occurs, these lamellar particles actually get sloughed off into the retinal pigment epithelial cells, and their job is to pull out the transretinal and reload with cisretinal and stick it back in there. So what that means is with time you can overwhelm the ability of your rods and cones to absorb light. It's called photobleaching, and all that means is that in a particular spot of your retina you've already chunked through all of these and you're waiting for them to be reloaded. So if you want to see how this is done, you know, turn on your flashlight on your phone and stare into it for a while, and then try to look where you were staring into it, and it will be difficult to see for a while. That's about how long it takes for the retinal pigment epithelial cells to recycle some of these particles and send them back in. Yep. Kind of cool. Nobody's actually doing it, right? Do you want me to turn on my flashlight and you can stare into it? All right, others? Let's see. Right, so when Jesus said the light of the body is the eye, and if that eye be darkness, how great is that darkness? Maybe he could have also talked about the light of the body is 11 cis retinal, and when it goes trans, then it's dark. I don't know. So that's vision. Now, there's a lot more we could say about conjugation, but I want to introduce the one reaction from chapter 12 that we're going to deal with. There is another reaction in chapter 12 that it's possible you may encounter in your future. We won't worry about it too much. That is simply the addition of molecules to dienes, and what happens is totally not surprising based on what you would expect from what we did in chapter 11. The only difference is when I add a proton to one of these double bonds, I get a resonance stabilized carbocation as a result. And so in my products, I can either get addition of the bromine there, we call this a 1,2 product, or I can get addition of the bromine, try that again, here, well, we'll just make it clear, and we'll call that a 1,4 product. Your text spends some time on this and talks about conditions where you can get 1,2 versus 1,4. I'm not really that interested in it. It's possible if you're going to be taking the MCAT or the DAT in your future that a reaction like this might be on it. So if you want to learn more about it, feel free to read it. I just don't think it's worth a lot of our time because it's basically everything that we talked about in chapter 11. Only if you know resonance, then it's no big deal. Okay? So I'm going to move on from that. The reaction I want to talk about today, I'm trying to decide whether you're going to hate it or love it. It is a famous Nobel Prize winning reaction. It's simple, but it rapidly leads to complicated products. So I'm going to give you a bit of a history lesson on how this was found, and then we'll take a step back, simplify the reaction so it's clear what's happening. We'll talk about how even in this complicated reaction, it's still just HOMO attacks LUMO, And then we're going to have to deal with all of the stereochemical and regiochemical issues associated with this reaction. So, Otto Diels and Kurt Alder were chemists in Germany. In 1928, they were awarded that's actually maybe not right. The Nobel Prize was awarded later. The discovery was in 1928. And they were doing a reaction with an interesting molecule, cyclopentadiene, and then this 6-membered ring molecule, which I'm not sure what it's called. It has a name, but we don't care. And they found that when they added heat, organic chemists, when they want to show that you add heat to a reaction, will often just use the Greek letter delta, I think, because from a certain point of view, it looks like a fire. Okay, so don't be surprised by the delta. But the products that they isolated from this, was really interesting. Do you hate it already? Make it stop. Okay, all right, and if you want to, we could draw this from the side, though I don't think that will make your life any better. I don't even like this. It's sort of hard to draw from this perspective. Okay. So go ahead and give your brain a moment to sort of rebel and say, what the heck and why is this even important, and I don't believe you and all of this stuff. Okay? It's actually an interesting question, which I don't know the answer to. How did they know that this was the product? We've got a lot of modern analytical techniques that we will talk about in the next little bit about how we know what the structures of organic molecules are. Those were a lot less available in those early years. And so identifying a complicated product like this and convincing the world that you'd actually made it was a big, big deal. Let's try to figure out what's changing here. And we're going to use color to highlight. Go ahead. I'm sorry, is there a specific reason why what? Well, they're pointing in opposite directions here. And so this, what I've tried to draw here is this 6-membered ring with the ketones on either side. And maybe it'll become clearer if I try to highlight the portions of the molecule that are from our starting material that are still present in the product. All right, so let's do the 5 atoms of cyclopentadiene. And, you know, sometimes when dealing with complicated products, it can be useful to number atoms. So I'm going to show you the numbers. I don't think I need 2 orange highlighters, do I? I'll change the color on that one. Right, so here is the portion of the molecule. Those are the in orange is the portion of the molecule that's from cyclopentadiene. Here are the atoms 1, 2, 3, 4, and 5. Alternatively, we can highlight them here. 1, 2, 3, 4, and 5. All right, let's do the other one. And we can number the atoms of the ring 1, 2, 3, 4, 5, and 6. Okay. And if we do this in our drawing here, there we go. I guess it would be good to point out that these two hydrogens on our purple molecule end up here. All right? Okay, so I realize that's hard to see when you're not experienced with this reaction. We're going to get you so that you're experienced. Go ahead.
So because there is that the 5-membered ring, which sort of almost becomes a sigma ring, the configuration of that mean that it doesn't have the up-down carbon mating? Just because when you learn about other 2 6-membered rings next to each other, both those actions.
Right. So I think the question is about you're noticing that whatever we've made, now you have 2 6-membered rings fused together. And the place you've seen that before this semester was back when we were talking about chair structures and trying to make things as painful as possible. And we talked about the difference between the conformations of these two molecules, both of which are valid, and one could flip and the other couldn't because of the ability to span the distance between two transaxial positions. Here it's a cis substitution pattern. You're going to see that the stereochemistry here at carbons 1 and 2 is entirely controlled by the stereochemistry in the starting material. In other words, you've noticed that these two protons are cis to each other in the product relative to the rings that they're in, and they were cis to each other here in the starting materials. Yeah. So we'll get there, but you're right. There is a connection between stereochemistry of the starting materials and stereochemistry of the products. All right, so those are that's where everything is. Now let's focus in on what bonds we made as part of this process. And I'm just going to look for bonds in the product that were not present in the starting material. So, for example, this pi bond in the product between 2 and 3, that wasn't present in the starting material. So that's one thing that had to change. The sigma bond between carbon 1 and orange 1 and purple 1 was not there in the starting materials. And the sigma bond between purple 2 and orange 4 was also not there in the starting material. So if I'm trying to keep track of the bonds that I've formed, I make a sigma bond between carbon 1 and carbon orange 1 and purple 1. I make a sigma bond between orange 4 and purple 2. And then I make a pi bond between orange 2 and orange 3. Does that look right? So let's look at the bonds that we lose. We're going to look at bonds in the starting material that are no longer present in the product. So I see a pi bond between 1 and 2. I see another pi bond between 3 and 4 that's not in the product. And then I see a pi bond between purple 1 and 2 that is also not in the product. Am I missing anything? That would be this one, and this one that we lose. Okay. So take a look at that. We're losing 3 pi bonds. We're replacing them with a new pi bond and 2 new sigma bonds. So based on your understanding of sigma versus pi bonds and their relative stabilities, is this reaction uphill or downhill in energy? Downhill in energy, or at least enthalpy. You might predict that because you're taking 2 things and linking them together that there might be a problem with entropy. We're not going to worry about that. We predict this reaction to be exothermic. Why? Go ahead. Sigma bonds are more stable than pi bonds. The bonds you form are more stable than the bonds you broke, therefore it's exothermic. Okay? And this is true for a lot of Diels-Alder reactions. One thing that you may have noticed, we only made really 1 new ring here. It's obscured by the fact that there were rings in our starting materials. But see the orange ring? We didn't really make that. That was already there. And the purple ring we also didn't really make. That was already there. The thing that we made is this new 6-membered ring that contains atoms 1 through 4 of the orange partner and atoms 1 and 2 of the purple partner. That is a 6-membered ring. And so now you can tell why organic chemists care about this, because we love 6-membered rings, and this is a way to make a decently complicated 6-membered ring in a single step. And people have used, the reason this reaction won the Nobel Prize is because people went on to use it to synthesize a large number of important natural products, and some of those I'll show you. Questions you want to ask so far? Yeah.
So heating it is the only treatment they.
Yeah, heating it is it's presumably to get over the activation energy to make the reaction happen is what they did. Sometimes this reaction isn't fast and you need to add something to help it along. That will make a little bit more sense once we talk about what's going on here in terms of homo-lumo-nucleophile and electrophile. Go ahead. Is this the only product that comes out of this reaction? This was certainly the major one, though you can imagine a stereoisomer that would follow all of the connectivity rules. This was major. And that stereoisomer would be simply and let's see. Erase, erase, erase. Right. Okay, so that's the other stereoisomer option. The only difference between these 2 options is the relative orientation of atoms 2 and 6 versus atom orange 5. That is, over here, purple atoms 2 and, well, that's a 3, isn't it? Okay. Is that driving some of you like, should say 3. Yes, 3 and 6 up here are on the same side of our new molecule. Dang it. 3 and 6 here are on opposite sides of our new molecule or our new structure versus orange atom 5. Do you see how relative to this new cyclohexane ring that we made, this group is up and these are down? Okay. In contrast, for the other stereoisomer, it's exactly backwards. Atoms purple 3 and 6 are on the same side of our new cyclohexene ring as is orange 5. What is the relationship between those two options? Yeah, it is a cis and trans issue. We have a word for isomers that are cis and trans. Are they enantiomers? Are they mirror images of each other? No. Are they stereoisomers? Yes. Therefore, Bob and Larry tell you it's an ape. It's a diastereomer. Yeah.
So does this have to do with the
Exactly. So the book talks about two different products, endo versus exo, and that's exactly what it's talking about here. This is the endo diastereomer, and this over here is the exo diastereomer. And the thing about endo versus exo, I suppose they could have called it cis versus trans. They chose endo versus exo, endo meaning in, exo meaning out. I don't know totally why they decided to assign them this way. Fortunately, there's a lovely mnemonic device present. If you draw the molecule from the side, and then, let's see, you've got orange atom 5, and then relative to orange atom 5, purple 3 and 6 are pointing down, like endo, down, I don't know. We'll talk a little bit about endo versus exo later, but it's essentially an issue of what the relationship between atoms 3 and 6 on the on this molecule, which we'll talk about what we're going to call that molecule in a minute. Atoms 3 and 6 on the purple molecule and atom 5 on the orange molecule. If they're on the same side of the new ring, it's an exo product. If they're on opposite sides, it's an endo product. Historically, endo tends to be the major product. There are various ways people have tried to explain that, and probably it's beyond the scope of what we want to do here, so I'll just ignore it. Right. Okay, yes?
Outside of this endo versus exo context, with all the other reactions, include both stereoisomers being viable?
So are both stereoisomers, I think your question is, on a test, do I need to draw both stereoisomers? And the answer is no, because you don't need to draw anything on a multiple choice test. I suppose that if I gave you both of these options as options for the reaction and you chose both of them, I could not criticize that answer or take off points for it. If you just showed the endo as the major product and chose that, I could also not take off points for that. Is that?
But outside of the endo exo context, would it be necessary to
I'm sorry, I guess I don't understand what you mean by outside.
as if it's not forming that double ring and it's another reaction,
If it's not forming a what membered ring?
or two 6-member rings, if it's just another one where the diamond power is different.
Okay, I'm sorry, I misunderstood your question. I think the question is related to, if I change the structure of these, could I still assign endo versus exo? Still no? I'm sorry, I'm so dense today. Okay, if you think of a way to say it that I can understand, explain it to me like I'm 5, and then maybe I'll get it, okay? You can think of it. And hopefully I'll show some examples that'll help in a little bit. All right. So let's just simplify all the connectivity issues. The reaction I'm going to show you isn't a particularly good reaction, but it's going to illustrate all of the connectivity changes that are going on in the Diels-Alder reaction. And it will give us a chance to sort of talk about HOMO and LUMO. So you can react these two together to make a cyclohexene ring. Here is the 4 atoms of our orange molecule, here are the two atoms of our purple molecule. And here are our new bonds that we make. There's the pi bond, there's the two new sigma bonds. And the product of a Diels-Alder reaction is always a cyclohexene ring. And so if you see a cyclohexene ring in a natural product, you can already be thinking, hey, I could have made that via the Diels-Alder reaction. Yes?
Are you saying this reaction that you just drew is a simplified Diels-Alder reaction?
Yes. This is an example of the Diels-Alder reaction. It doesn't work particularly well, but it illustrates the connectivity that's changing. All right, let's talk about reactive partners. It gets a little tricky talking about which of these is the nucleophile and which is the electrophile. And it turns out that it doesn't matter actually which one you say is which. I'll maybe try to illustrate that. People tend to call we call this molecule a diene, a 1,3-diene. So now I get to tell you a dumb chemistry joke. Help, I'm dying. Right? Yes. Yeah, I got teenagers. Groans is all I get at attempts at humor, so that's all right. All right, and we call the other partner, you can call it the olefin, which is fine. You could call it the alkene, but that's entirely too much nasally "ene" stuff going on, so I prefer either olefin, or if you want to make your life really hard, people call this the dienophile because it is the thing that reacts with the diene. For our purposes, we're going to pretend like the diene is the nucleophile and the olefin or the dienophile is the electrophile. You don't have to think of it that way, but let's at least start there. Okay, so nucleophile and electrophile, HOMO and LUMO. What is the LUMO of the olefin? It has to do with the pi. You got two choices, pi antibonding, pi star. Okay, good. If we were to draw that pi star looking down on the molecule, it would have a node in between the two carbons, 1 and 2, and there would be a switch in wave function sign. And we're looking down, and so below the plane of the page, you would have the other lobes of the p orbital. If you wanted to look at this molecule from the side, that's fine. You would draw the pi star like this. Okay, that should be fairly familiar to you. You okay with that? Yes, good. All right. How about, and this may be a little trickier, how about the HOMO of the diene? And this really is why we spent some time talking about conjugated pi systems and what the HOMO and the LUMO are. You've got 4 atoms here involved in conjugation. So I really should have 4 pi molecular orbitals available. 1, 2, 3, and 4. I'm just going to write down atoms 1, 2, 3, and 4 here. I know that in the lowest energy orbital there should be 0 nodes, and then I can sort of build up from there. There should be 1 node here, 2 nodes here, and 3 nodes here. I know that in my conjugated system I have 4 electrons. So that means I've got 4 electrons involved in conjugation. That means I'm going to fill pi 1 and pi 2, but pi 3 is going to be empty, and so pi 2 is going to be the highest occupied molecular orbital. You with me so far? We don't even need to know what that orbital looks like yet, but we know the HOMO is going to be pi 2. Right. So for 0 nodes, the way this orbital is going to look is a lobe of electron density above the plane of the sigma bonds and a lobe below the plane of the sigma bonds, with no change in wave function sign as you go from left to right. Sometimes people will draw this with what I'm drawing now is a schematic way to draw the same thing I just drew on the left. You okay with that? Am I confusing anybody? So with one node, we would put the node right in the middle between 2 and 3. We would have a lobe here and another here and there. And there would be a wave function sign change between atoms 2 and 3. I think I need more space. Good enough. So schematically, if I were to draw this this pi 2, excuse me, orbital, it'd be like this. I'm, by the way, not going to ask you to generate these pi orbitals from scratch as I'm doing here. I would, like I've done on the practice exam, give you a series of pi orbitals and have you assign HOMO versus LUMO.
Will the nodes always be evenly splitting things?
Do the nodes have to be evenly splitting things? Yes, there are symmetry requirements for these orbitals. So yeah, there's a reason I put the one node in the middle. It actually just falls right out of the math of MO theory, but you can think of it as a requirement. So the third one looks something like this. Which, if we were drawing it schematically, we would have done this. And then the next one, the highest energy one, is the one that has 3 nodes in between, a node in between each of the atoms, and that would be each of the p orbitals lined up, but with a change in wave function sign between each of them. All right. Thoroughly bored? Man, I'm losing circulation in my hand. Maybe I need to grip the pencil less tightly. All right, so if we were to draw on the diene what the highest occupied molecular orbital looks like, pi 2 is the HOMO, so I'm going to attempt to draw pi 2. There's going to be a node in between atoms 2 and 3, and a change in wave function sign. Let's see. Okay. So, question for you. What do you notice about the wave function signs associated with these 2 orbitals? And let me just preview this by saying atoms 1 and 4 on the diene are going to be the ones that have the new sigma bonds associated with them, and atoms 1 and 2 on the olefin or the dienophile are going to be the ones making the sigma bonds. What do you notice about the relationship between the portion of the orbital of the HOMO on atom 1, orange 1, versus the portion of the orbital from the LUMO on purple 1. Same wave function sign, right? And notice that the way this works with the LUMO, purple 1 and purple 2 are going to have opposite wave function signs on them. Right? There's going to be a switch because of that node. Similarly, orange 1 and orange 4 are going to have opposite wave function signs on them. And it just so happens that this allows for orbital overlap between purple 1 and orange 1 and between purple 2 and orange 4 without, in a constructive interference way, without a change in wave function sign as we make the new bonds. In other words, you've talked about before how we make a new bond by end-on-end overlap of, say, an sp3 orbital with a 1s orbital from hydrogen. We bring them together, we make a new bond. And the plus bonding combination is the one where the wave function signs match. What I'm intending to show you is that the HOMO of the dienophile and the LUMO, the HOMO of the diene and the LUMO of the olefin are able to come together with the same wave function sign and engage in that productive bond-forming orbital overlap. Okay? It'd be nice if the clock worked, right? It's always 3:13. And on the PowerPoint, it's always 9:41 on, yeah. It would have been funny, actually, if they could make this glitch so that it would always be Groundhog Day in that title, but no. All right, so let me show you how this reaction actually happens. So you're going to have to work on your 3D reasoning. Let's draw the diene as though we're looking at it sort of standing on its end, standing on carbons 2 and 3. So maybe you're going to hate this. It's okay. As I tell my primary children, I don't care if you hate it. That's right. So I'm going to draw the LUMO of this molecule. That's terrible, isn't it? I still don't care. All right, so we've got the node in between carbons 2 and 4. The important point, though, is that the wave function sign for carbon 4 is opposite what the wave function sign is on carbon 1. Whoa. Okay, so we've tilted this diene on its side. That's what we're looking at. Sort of got it? Ish. Sorry, it's terrible. I realize this. Now we'll draw the olefin on its side. Here's atoms 1 and 2. Yeah, not very good. Okay, and let's see. I will choose pink here. All right, so the pi system of the diene is going to approach the pi system of the olefin or the dienophile as HOMO attacks LUMO. And what do you see there? Perfect orbital overlap in phase with direct wave function sign, okay? Kind of nice. So this is how the bond forming process happens. I'm going to draw dotted lines to indicate the bonds that are forming. All right? Now, I told you that it actually didn't matter whether you thought of this reaction as diene being the nucleophile and olefin being the electrophile. Let's just, real quick, take the situation and reverse it. Suppose I wanted to think of the diene as the electrophile. And suppose I wanted to think of the olefin as the nucleophile. For the olefin, what would the HOMO be? Simply be the pi orbital, right? Which we could draw from our perspective. Purple atoms 1 and 2 there would be no switch in wave function sign between the two of them. Man, that's terrible. All right, then what would the LUMO have been for the diene, our electrophile? Look up there, it's pi 3, which if we were to draw, would be something like this. Sorry, that's kind of yuck. Do you notice how, and it may take a minute for you to confirm that I'm just drawing here sideways what we drew here. Do you notice that when we pretend like the diene is the electrophile and the olefin is the nucleophile, do you notice that we still get correct end-on-end overlap? Yeah. So it turns out that that's a perfectly valid way to think of this reaction too. And if you pay attention to what's going on in this reaction, there's 3 pairs of electrons that are moving. And we'll usually push arrows like this to indicate forming the first sigma bond, this to indicate forming the second sigma bond, and this to indicate forming the pi bond. Okay? So what I just told you was that in this process, sorry, the payoff I hope is good. It probably isn't, let's just be honest, but I believe in you. All right, so think about how this reaction happens. You can have HOMO on the diene attack LUMO on the electrophile, on the olefin, and wave function signs on either end match. You can have HOMO on the olefin attack LUMO of the diene and wave functions match. Here's the third pair of electrons that's involved. It's in this lowest energy pi 1 orbital. What do you suppose that's going to look like once we finish up and we've made sigma bonds here so that 1 and 4 are no longer sp2 hybridized? Those are the ones that are still hanging out between atoms 2 and 3 as the pi bond, right? It's like you cut off the terminal atoms there and they're still there. So even though, what I'm trying to show you is even though in our mechanism we'll show 3 arrows happening, there's really just 2 things happening. HOMO attacks LUMO, and then this one just stays where it is, now it's only between 2 and 3. All right, that was not a decent enough payoff, but it'll give you something to think about till Friday, where we will unleash all of the stereochemical and regiochemical issues associated with this reaction. See you then.